I'll start off this video lecture by reminding us of where we're at. What we want to do is master the fine art of proof construction. In assignment 5, exercise 4.2, we're starting with the simplest possible scenario. There are just 4 multi-line basic rules that you set up for. You might not have been aware of it at the time, but there's a pretty limited range of proofs that we can construct when we're limiting ourselves to just those 4 rules. But it was a good way to start off with this new activity of line-by-line proof construction, where every new line is an application of one of the obviously valid rules to some subset of our available data. In assignment 6, we expanded our rules to the full basic 8 rules. There, it's important to be aware that 5 of the 8 basic rules can be thought of as multi-line basic rules that you set up for. What these rules do is they use information from more than one line in order to infer new information. Simplification, addition, and conjunction, in a very limited range of cases, can also be used to infer information, but by and large, they're the basic rules you set up with. So assignment 5 and 6 are primarily designed to thoroughly acquaint you with this activity of proof construction. We're now at assignment 7, where we've expanded our range of logical rules once again to include the 10 equivalence rules. All 10 of these equivalence rules are ultimately rules that you use to set up for the application of one of the multi-line basic rules. There were exercise 4.6, which focused on De Morgan's and double negation, exercise 4.11, which focused on commutation, association, and distribution. Exercise 4.8, 4.12, and 4.13 are ones where you use the full complement of 18 rules, the 8 basic and the 10 equivalents, to construct proofs. As I had said in the last video, I'm going to use questions from other textbooks so that I can leave as many of the exercise questions for you as possible. I've used up a few of the exercise questions in illustrating, but from here on in I'm going to use questions that are different from the ones in the exercises. We can start with the following situation, which is a little bit uncommon in that we've only got one premise or one item of information. In cases like this, you're obviously not going to be using the multi-line basic rules because there only is one line of information. In a situation like this, the procedure for deriving the conclusion from the single premise is a little bit more difficult to standardize. It's generally going to involve some combination of the equivalence rules along with the basic rules that are most generally used to set up for the multi-line basic rules. Here, all we have is a biconditional. K, if and only if H. From that, we're asked to derive tilde H or K. In a sense, the first step is easy because there only is one rule for the biconditional, namely equivalence. And equivalence, if we use the top version, allows us to split any biconditional into a conjunction of mirror-imaged conditionals. The conjunction, of course, is very user-friendly. It allows us to snap off whichever conjunct is most useful to us, or if both are useful to us, it allows us to snap off both of them. In this case, however, only one of them is going to be useful to us. If we look up at the conclusion, what we want to derive is the disjunction tilde H or K. What we have are two conjunctions. Hopefully you're familiar enough with the rules that you recall the rule that enables us to transform conditionals into disjunctions, namely implication. The question though, which of these two conditionals is going to be useful to us in deriving that particular disjunction? The answer is the one on the right, H horseshoe K. Now, if you haven't familiarized yourself thoroughly with it, if we do an implication going from the left to the right, we can derive the assigned disjunction. So we've got a fairly short proof. The steps are equivalence, a derived or equivalence rule, simplification, one of the basic rules that you generally set up with, and finally implication, another one of the equivalence rules. This is a little bit unusual as far as the sequence of rule employments that we do, and it's because we've only got a single premise that we're working with. These situations do arise, and a familiarity with the rules is generally the most helpful thing you can have going for you. At this point, we can consider a fairly simple example of the much more typical situation where we want to strategically combine some selection of equivalence rules and or the basic setup rules in order to employ one of the multi-line basic rules. Now, when we're setting up for this application of a multi-line basic rule we set up for, what we want to do is combine similar kinds of information. This might seem like overkill in this very simple situation, but the method I'm going to describe for you can be used regardless of how complicated the proof construction situation gets. And as we begin to consider increasingly complex proofs, it's going to be important, or maybe I should say advantageous, to be much more organized in the way that we construct proofs. So we don't want to be any longer blindly searching for rule employment opportunities. Hopefully, we've familiarized ourselves with the various ways the rules can be employed, although we can continue to learn that when it comes to the equivalence rules. But we now want to be increasingly strategic in our rule employments. If we look at this proof, in the premises we have both A and B related information. In the conclusion we have A related information. So one way of understanding what we want to do is we want to make use of and at the same time get rid of the B related information. And the way we're going to do that is by strategically transforming the information so that we can apply one of the multi-line basic rules. The more familiar you become with proof construction, the easier, the more natural this process will become. With that in mind then, what we want to do is combine the B-related information in lines 1 and 2 in accordance with one of these basic rules. In order to achieve that goal, the first thing we're going to do is a De Morgan's on line 1. You can think of De Morgan's as an unlocking rule. If you have a negated conjunction, that information is locked inside the brackets and can't be used until you unnegate that sentence. De Morgan's is a useful way of unlocking these negated sentences. Look at the De Morgan's template if you need to. Any negated conjunction will become a non-negated disjunction where each of the two sentences has a tilde added to it. Tilde A or tilde B. That was a substantial step towards the process of making use of and at the same time getting rid of the B-related information. In line 3, we have a disjunction with tilde B as one of the disjuncts. In line 2, we have the sentence B. We're close to being able to carry out a disjunctive syllogism, but there's just one more adjustment that needs to be made. To double negation will give us tilde tilde B. So now we have the negation of the right disjunct, so that 3-4 disjunctive syllogism gives us tilde A. If you've already done the exercises in 4.11, we're already familiar with this process, but we haven't looked at it in quite this way. We haven't analyzed the sequence of steps that led us to the conclusion in this strategic way quite yet. So we had 2 equivalence rule steps as setups for the disjunctive syllogism step that makes use of the B-related information. And notice at line 5, there is no B-related information. So what we did in the disjunctive syllogism step that we set up for is we made use of and at the same time got rid of the B-related information and ended up with the A-related information. So that's a nice simple example of the strategy we're going to be employing in a gradually more and more complex way as we consider various proofs. Here's another fairly basic situation where we've got 2 instances of S-related information, and we also have an instance of Q-related information. So what we want to do is set up for the employment of one of the multi-line basic rules that you set up for, which is going to allow us to simultaneously make use of and at the same time get rid of the S-related information. We've got a biconditional in line 1, and remember there's only one biconditional rule, so this is fairly straightforward. Equivalence will give us S horseshoe Q and Q horseshoe S. So given that we given that we have tilde S in line 2, which of the two conditionals in line 3 is going to be of use to us? Not the one on the left, because having a conditional S horseshoe Q and the negation of the antecedent doesn't give you information that will enable you to validly derive any information. If we have tilde S and the conditional on the right, however, then we have a conditional and the negation of its consequent, and that information allows us to validly infer the negation of the antecedent by the multi-line basic rule that you set up for modus tollens. 2 for modus tollens gives us tilde Q. We can now consider a slightly more complicated situation. Here we've got two premises, but what I want to focus on is the fact that we've got F, G, and H-related information. And what we need to do is make use of and get rid of the F-related information as well as the H-related information in order to end up with the G-related information. So what we're going to have here is a proof that has more than one stage. And what I mean by stage is a sequence of steps that sets up for the application of one of the multi-line basic rules. So these rules are going to be the stage ending rules, and some combination of the equivalence and basic rules are going to be the setup rules in a particular stage. In this particular proof, the information is such that we have to proceed with the F stage first, since the second occurrence of the H stage is inside that bracketed disjunction. So, with that in mind, one simplification gives us F, then a double negation, not on line 2, but on line 3 will give us tilde tilde F, and the simplification in line 3 and the double negation in line 4 are the two setups for the stage ending disjunctive syllogism move. 2-4 disjunctive syllogism will give us tilde H. So We can think of that as the F stage, meaning by that the stage where we make use of and at the same time get rid of the F-related information. Now we can move on to the H stage, where we make use of and thereby get rid of the H-related information. Here we can do a second simplification to get the disjunction G or H, and that's all that's necessary to end off with a second disjunctive syllogism, 5 and 6, to give us G. So that's the H stage. One other thing I should point out here, there's no requirement that the proof be done in very neat stages. I've just done it this way in order to, as clearly as possible, set out this organization strategy for you. And I admit it might seem like overkill in a proof that is this short. It's only 5 lines. So you might have done 2 simplifications in a row on line 1. There's nothing wrong with that. It's just that you would be making the overall organization of the proof a little messier than it might otherwise be. And that's hardly a problem with a proof that's only 5 lines long. When we start to get to longer proofs, though, it'll be much more advantageous to keep the stages neater, just to make your own mental work easier. So here we had 2 separate subtasks that were completed strategically. The first subtask, making use of and thereby getting rid of the F-related information, then making use of and thereby getting rid of the H-related information. Here's one that's a little bit trickier. We've got 3 premises in this proof, and we've got, I'll put them alphabetically, H, J, M, P, and R related information. So we've got information pertaining to 5 different simple sentences in this proof. We want to make use of and thereby get rid of the H-related information, the J-related information, the P-related information, and the R-related information, so that we end up with the M-related information. Here, don't panic, just be logical and organized. Which stage should we do first? The H, the J, the P, or the R? Perhaps, looking at this information, you're just not sure. Well, is there any rule application that you can carry out? Here's an example. We've got the negated disjunction in line 3. So we can unlock that negated disjunction with a De Morgan step. So the disjunction that's negated is P or tilde J. So when we remove the tilde and the brackets, we end up with tilde P and tilde tilde J. Now we've got a user-friendly conjunction. Does that help us? If we look at the proof, there is no more P-related information, but there's J-related information in line 1, so we can snap off the right conjunct, tilde tilde J, for simp. What we've done is, so to speak, in these two steps, we could call this a P stage, where we didn't make use of and get rid of the P-related information. Rather, we just got rid of it by abandoning it. That is to say, not bothering to extract it from the conjunction in line 4. So sometimes we will have these stages where we're not both making use of and getting rid of, but we're just getting rid of by abandoning. That being said, now we've got tilde tilde j in line 5, and the other piece of j-related information is in line 1. Tilde j and r, if that, then h. Here's where an understanding of the equivalence rules is very, very helpful. There's one thing we can do though. If you notice, j is just by itself in line 1, so it won't hurt to do a neatening up of tilde tilde j to convert it to j. What we need to do at this point, and this requires familiarity with the rules, is an exportation on line 1. Look at the template, P and Q horseshoe R. Exportation entitles you to validly infer if P, then if Q, then R. In this example, if J, then if R, then H. Now, we could do 6, 7 modus ponens to get R horseshoe H. We could follow that by 8, 2 modus ponens to get M. But just to illustrate, I'm going to, well, I'll do it this way. 6, 7 modus ponens will give us R horseshoe H. So there's our J stage, and 2, 8 modus ponens is our first example of something that occurs reasonably frequently, and whenever it does occur, it's kind of a helpful bonus. What we have when we do 2, 8 modus ponens to get M is a double stage, so to speak. We are simultaneously, when we do the modus ponens on 2 and 8, making use of and getting rid of both the R-related information and the H-related information in one fell swoop. So there's no requirement that each of the stages involves making the use of and getting rid of a single letter. There could be, and there often are, multi-letter stages. And the other thing we saw with the P stage here is sometimes you're just getting rid of information that's not going to be of use to you in demonstrating that if the premises are true, then the assigned conclusion is true. So there's an example of a slightly more complicated proof, and I just want to again emphasize that organizing the way in which the proof proceeds stage by stage is a way of making your life easier, because what we've really got are some shorter, smaller, easier stages. Instead of having to think through the string of steps all the way from 4 to 9, you can think of it as 3 simpler or smaller stages. We'll consider consider one last example of this strategy in action, but before we do so, I'll just set out formally the strategy that I've been illustrating in the last few proofs. This is one proof construction strategy. We might call it the make use of / get rid of strategy. This is a top-down strategy. And what I mean by that is we start with our premises and in a systematic way we work downwardly until we arrive at the conclusion. With this strategy, we start by setting out all the different types of information that's available in the premises, and the different types of information will be indicated by unique uppercase or capital letters. For example, in this proof here, we've got C, D, and E related information. What we want to do is make use of the D related information in order that we can arrive at a conclusion containing C and E related information. The second part of the make use of / get rid of strategy is stage by stage focus on making use of any duplicated instances of letters that are not in the conclusion. In the conclusion, we've got C and E related information, and we've got 2 instances of the D related information. For letters that are not in the conclusion that occur only once in the proof, rather than making use of them, we will just be getting rid of them. And finally, in many situations, once we've arrived at information containing only the letters in the assigned conclusion, we may have to reconfigure the information containing only letters in the conclusion. So it's very important to, in the background, be aware of the big picture, of exactly what you're up to in the proof. So, we start this proof. We're not just blindly looking for rule employment opportunities. Rather, we're focused on the sub-goal, now that we've ascertained that we've got C, D, and E related information. C and E related information is in the conclusion, of making use of the D related information. Here, we've got a locked conjunction. The second premise is a locked disjunction. So, this particular proof calls for 2 De Morganses in a row. The first one, on a negated conjunction, is going to give us tilde C or tilde D. The second one, on a negated disjunction, with one of the disjuncts negated, is going to give us tilde, tilde, D, and tilde E. So we can snap off tilde, tilde, D, a simplification step that sets us up for a disjunctive syllogism. That's the step that ends the stage by employing one of the multi-line basic rules we set up for. 3-5 disjunctive syllogism gives us tilde C. Now we can snap off tilde E, which is 4 simplification. So we've got our C and E related information on line 6 and 7. We can combine them into a single line of information using the conjunction step. Finally, given the information we have, in this particular proof, we will reconfigure our C and E related information by carrying out a third De Morgan step to give us tilde C or E. Here's another simple proof where we can consider an alternative proof construction strategy that's called the backwards planning strategy. Unlike the make use of / get rid of strategy, which is top down, the backwards planning strategy is bottom up. Here's the general idea. Given the information available in the premises, determine the sentence you're going to need in the second last line of the proof in order to derive the conclusion by a single rule application. In other words, if you're at a little bit of a loss as to how to start the proof, often it's much clearer how the proof is going to end, and you can figure out the sequence of the steps in a backwards, bottom-up manner. So once you've determined the sentence you need in the second last line of the proof, in order to derive the conclusion by a single rule application, then you just make the same determination for the third last line of the proof. What do you need in the third last line of the proof to derive the second last line? And so on. Normally, and when the proofs start getting longer and more complicated, and that's the kind of situation where the backward strategy plans off, this board will be blank so that I can do the backwards planning beside the proof I'm actually constructing. This is just for initial illustrative purposes though, and the proof is short enough that we can chart out the backwards planning underneath here. So the sentence we want is S. Given our information, where the S-related information is the left disjunct in a disjunction, the idea is if we could just get tilde P as the second last line of the proof, then we could get our conclusion by disjunctive syllogism. Now we focus in on the second last line of the proof. Given our information, how are we going to get tilde P? Answer, since the P-related information is the antecedent of a conditional, we're going to get tilde P by modus tollens, and what we would need to get tilde P by modus tollens is the negation of the antecedent, namely tilde, then in brackets, G and R. How are we likely going to get tilde G and R? Given that it only occurs as the consequent of a conditional, about the only way we could get that is by De Morgan's. Then we ask ourselves the question again, what would we need as the fourth last line of the proof in order to get tilde G and R by De Morgan's? Because once we get that, we can get tilde P by modus tollens and get our conclusion by disjunctive syllogism. We would need the disjunction tilde G or tilde R. We look at our premises again. We've got tilde G, so the way to get tilde g or tilde r is just by addition. So in this example, instead of planning our way downward, making rule applications on the basis of our initial premise set and gradually enlarging the information, we're using an alternative strategy where we're charting out how the proof is going to end. So we're working our way backwards. This is the bottom-up strategy. And as this simple example illustrates, the bottom-up strategy is often very useful in indicating sequences of steps that may not occur to you when you're looking at the proof from a top-down perspective. Now we see, though, as a result of our backwards planning, that the first step of the proof is tilde g or tilde r. So that's 3 addition. So ask yourself, would that have occurred to you as the first step of the proof? If not, then this backwards planning strategy provides some insight. And now we can move on. The reason for doing that addition step, and remember, there's always got to be a reason for doing an addition step. There's way too many allowable addition possibilities. You only want to do ones that you have a reason for doing. And we certainly have a reason for doing this one, which was revealed by the backwards planning. Having done the addition step, when we do a De Morgan's, we're going to end up with the negated conjunction, tilde g and r. And now, 2, 5, modus tollens. So, from a top-down perspective, we've got an addition step followed by a De Morgan step, 2 setup steps for the modus tollens. The important thing to emphasize here, though, is these 2 steps might not have occurred to you, and it's much easier to figure out that these 2 steps are the way to go if you adopt the backwards planning mode. And having done that, the final step is straightforward. 1, 6, disjunctive syllogism, which gives us S. So, very useful kind of strategy. Hopefully, if you're advancing enough in proof construction, you might have thought your way through how to construct this proof on your own without the backwards planning, but very important to be aware of the backwards planning strategy, because when proofs get longer and more difficult, this proof will often make, this proof construction strategy, backwards planning, where you're planning from the bottom up instead of the top down, can make your life a fair bit easier. We can now consider a subgenre or subcategory of the backwards planning strategy. This particular proof, when you look at it, doesn't look like it should be all that hard, but from a top-down perspective, it's going to be really tricky. On the other hand, it's not as if the move to a bottom-up strategy is going to completely eliminate our problems. If that's the final line of the proof, it might seem like we still don't have much insight into how to plan the proof from the bottom up either. At this point, I can point out a general sort of principle having to do with distribution, namely, whenever you can't figure out how else to do a proof, it's pretty likely that there's going to be a distribution involved. So distribution is a sort of rule of last resort. This is why it's very important to master distribution, because there are certain proofs where you need it. So, if we decide we're going to do a backwards planning because we just can't figure out how to solve this proof from the top down, and there's a distribution involved, is that going to get us anywhere? Yes, it will, because if you think about distribution, it's a set of rules where you go from a conjunction to a disjunction, or a disjunction to a conjunction. And what this tells us is that if we want to get a conditional and there's a distribution involved, we're probably going to get that conditional by implication. So now we can ask ourselves, what would the second last line of the proof have to be in order for us to get this conditional by implication? Answer, it would be tilde, T or S, or G. So if we could just get that disjunction, then by implication we could get our final conditional. How are we going to get that disjunction? Here, notice that we've got a negated disjunction. How are we going to get that disjunct? Answer, by De Morgan's. Very important that all of the equivalence rules apply to parts of lines or entire lines. So this part will stay exactly the same. What would the third last sentence of the proof have to look like in order for us to get this one by De Morgan's? It would have to look like this. Tilde T and tilde S. How are we going to get this sentence, given that there's going to be a distribution involved? Hopefully you're familiar enough with the distribution rules to see how things have to work at this point. If there's a distribution involved, we would have to get this sentence by commutation from this one. G or tilde T and tilde S. How are we going to get this sentence? This is the one that's going to come from distribution. If you look at the distribution template, this is the one on the bottom left. P or Q and R. What are we going to get that sentence from? We're going to get it from the conjunction P or Q and P or R. In other words, we're going to get it from G or tilde T and G or tilde S. So if we could just figure out how to get that conjunction, then we'd know how to get this disjunction by distribution. Commutation, we'd switch it around, then De Morgan's, then implication, we could get the conclusion. Well, not surprisingly, we're going to get this conjunction by the conjunction rule. And what that's going to mean is we just have to get both of the conjuncts separately. Hopefully, at this point, when you look at our available information, the way to proceed will come to you. So we want to get G or tilde T. Can we get G or tilde T from the conditional T horseshoe G? Yes, we can, and that's going to require two steps. The first thing we do is one implication to give us tilde T or G, then three commutation to give us G or tilde T. So that gives us the left conjunct in the conjunction we're after. The right conjunct is also going to require two steps. Tilde S or G is going to be two implication followed by five commutation. We now have the two conjuncts in the conjunction that we're after. So, as has been revealed to us by our strategic backwards planning, G or tilde T, once these become conjuncts, they'll have brackets around them. G or tilde S is just going to be 4, 6 conjunction, and now we can do the all-important distribution step where we're going to go from the bottom right to the bottom left. So we're going to end up from the conjunction with the disjunction G or tilde T and tilde S. So that's 7 distribution. Then, as planned, because we're aiming for that conditional, tilde T and tilde S or G is going to be 8 commutation. Then we're going to switch this conjunction of two negated sentences into a negated disjunction, so that's 9 De Morgan's. And that's just what we need to finish off the proof. 10 implication. If T or S, then G. So that's a fairly tricky proof to prove from the top down. You'd have to be very familiar with the rules, and indeed, in order to construct a proof like this from the top down, you have to have a plan of how things are going to end, which you might keep in your head, but certainly at our stage here, you can make your life much easier by engaging in some strategic backwards planning. Here's another one that's kind of tricky. This is a proof where when you look at it, it seems like it should be really straightforward. We've only got one premise, but that premise tells us if Q is true, then both W and D are true. So from that, it should, it would seem, follow pretty straightforwardly that if Q is true, then W, one of the two conjuncts in the conjunction that's the consequent of line 1, is true. How do we prove that, though, given our 18 rules? Answer. We need to realize that, after staring at the paper for some time, there's no other way to solve a proof like this except by distribution. So, if we can't solve this proof except by distribution, and the final conclusion is Q horseshoe W, how are we going to figure out the second line? If you are familiar with the distribution templates, the way in which we're going to get that conclusion from something that comes from a distribution strategy is by implication. So that means if we could just get the disjunction tilde Q or W, how are we going to get that conclusion given the single premise that we have? Here, familiarity with the rules is crucial. The way we're going to get a sentence like this is by simplification from a conjunction of two sentences, namely tilde Q or W and tilde Q or D. That's the sentence that's going to come by distribution. What would we need to get a sentence like this by distribution? Answer, well, we'd need the following disjunction. Tilde Q or W and D. At this point, hopefully, the light goes on in your mind and you realize that we can get this sentence by implication from our original premise. So, with that in mind, we can proceed. 1, implication, tilde Q or W and D. So that one implication gives us a sentence of the same form than the bottom left of the distribution template on page 13 of the notes. And once we do distribution on that, as we've planned out before, we're going to get tilde Q or W and tilde Q or D. And given that the conclusion we're after is Q horseshoe W, we will snap off the left conjunct, the one that's going to be of use to us, and we can end the proof as planned for implication to get Q horseshoe W. So this will end the video lectures for this week. At this point, you should be proceeding through the various exercises in assignment 7. So that is exercise 4.6 that emphasizes double negation and De Morgan's, exercise 4.11 that emphasizes commutation, association, and the all-important distribution. Then exercise 4.8 and 4.12. I can't emphasize enough that you're not going to succeed in this class by trying to memorize the answers. What I've given you are just some basic proof construction strategies that hopefully will enable you to more efficiently learn for yourself how to apply various combinations of these 18 rules in a strategic way where you begin to analyze the information in terms of those rules. So the real goal that you need to be striving towards as you do the exercise questions is familiarity with the rules, familiarity with analyzing information or premise sets in terms of these 18 rules, as well as familiarity with this. Hopefully it's not such a new task anymore of strategically manipulating the data in information sets, that is premise sets, in accordance with some combination of these 18 valid rules in order to conclusively demonstrate that if your initial information set is true, it's impossible for the assigned conclusion to be false.